Welcome to This Explainer. If you're anything like me, you've probably looked at modern AI systems, from chatbots writing these incredibly elegant essays to algorithms diagnosing complex diseases and felt, well, a little intimidated. We trust these systems with our lives on the highway, yet most of us have absolutely no idea what's actually happening inside. It all feels so mysterious, doesn't it? Kind of like there's some sort of digital magic happening behind closed doors. But today, we're going to pull back that curtain. We're going to demystify that black box and look right at the fascinating, microscopic mechanics that make these incredible systems work.
So, let's dive right in. When you see a self-driving car effortlessly navigating a busy, totally chaotic intersection, or an AI instantly translating a foreign language in real time, what exactly is happening inside that black box? How do these systems actually think under the hood? You might expect a web of code so tangled and complex that you'd need 3 PhDs in computer science just to decipher a single line of it. But what I've found is that the reality under the hood is actually shockingly different. I absolutely love this quote from machine learning educator Victor Zhu. He says, "Neural networks aren't that complicated." Now, I know that might create a little immediate cognitive dissonance for you. Like, how on earth can something that drives a 2-ton vehicle at highway speeds not be complicated? But it's true. The secret here is that AI isn't magic. It's just beautifully layered, relatively simple math, repeated millions or even billions of times over. To put this into perspective, think about how our own minds work compared to these artificial models. Our biological brains are beautifully, wonderfully messy. We deal with unstructured, chaotic data from the real world, and we're learning continuously in a very organic, electrochemical way. Artificial networks, on the other hand, they are strictly, highly structured. They process information in rigid, defined layers, they use cleanly weighted numerical data, and they generally operate in these very distinct, gated training phases. So they're digital, computation-based models heavily inspired by the human brain, but ultimately they're purely mathematical simulations. They rely on order rather than organic chaos.
But we didn't just wake up to ChatGPT overnight. This whole thing is actually an 80-year evolution. It started way back in 1943 when Warren McCulloch and Walter Pitts created a mathematical model of a single binary biological neuron. It was essentially just a simple on or off switch, but it was a massive conceptual leap. Then in 1958, Frank Rosenblatt created the perceptron, which was the very first truly trainable neural network. Fast forward to today, and we have modern deep learning, which is quite literally scaling those exact same foundational ideas up to trillions of parameters. The math hasn't changed its core identity, it's just grown exponentially. Section 1. The microjourney. Processing a simple input.
Okay, to really grasp how these networks process simple inputs, we need to zoom way in. We're going to plunge microscopically into a single artificial neuron to watch how data actually flows through it. Imagine we're feeding this neuron some incredibly simple data, let's say a person's height and weight, flowing in as raw numerical particles. How does this single node handle that continuous flow of information? Well, it operates in a very kinetic 3-step mechanical process. First, the incoming data is multiplied by a weight. Think of a weight as a physical dial controlling how important that specific input is. Maybe a person's weight matters way more than their height for the specific prediction this neuron is trying to make, so the network turns the weight dial way up, amplifying that number. Second, we add a bias. A bias is really just a built-in value that shifts the neuron's decision threshold, giving it a sort of baseline inclination. And finally, the sum of all those numbers is passed onward to step 3.
Right, so the final step here is the activation function. You can kind of think of this as a mathematical funnel. See, when you multiply those weights and add those biases, you could easily end up with massive chaotic numbers. You could have -1,000, +10 million, you name it. If neurons constantly passed around unbounded numbers in the millions, the entire system would instantly overload, destabilize, and just break down. An activation function, like the really commonly used sigmoid function, solves this completely. It takes that unbounded mathematical chaos and neatly funnels it into a clean, predictable range, typically squishing any wild number down to a neat little decimal between a 0 and a 1.
And here is the absolute climax of this entire mathematical chain reaction. After the data comes in as a particle, gets amplified by those weight dials, has a bias added to shift the baseline, and gets squeezed through that mathematical funnel, it spits out a concrete decimal number. In a beautiful example from Victor Zhu's research, an input of 2 and 3 simply resulted in the number 0.999.
That's it. That's the output of all this supposed digital magic. It's just a concrete, simple decimal number representing a tiny prediction or a localized piece of insight. Honestly, it's astonishing when you realize that is literally all a neuron is doing.
Section 2. Building the network. Feed forward.
So, now that we've mastered how a single neuron processes simple inputs at the micro level, let's zoom back out a bit. A single neuron giving us the number 0.999 is super neat, but a single decimal isn't exactly going to drive a car or translate a book. To do that, we need to link these individual neurons together. This is where we build the network, and the process of passing these numerical outputs forward from one neuron to the next is called feed-forward. Information in a feed-forward network moves continuously from left to right, kind of like flowing energy. It starts at the input layer and then moves into what are called hidden layers. You can picture these hidden layers as a highly efficient assembly line. The very early layers might just notice incredibly simple patterns, a vertical edge here, a tiny change in texture there. But as that information is mathematically combined and passed forward, the deeper hidden layers start to recognize much more complex concepts. An edge becomes a shape becomes a wheel, and eventually a wheel becomes a stop sign or a human face. Complexity literally emerges from simplicity.
Which brings us to Section 3. Learning from mistakes. The stupid brain. So how does the network actually know what the right weights and biases are? Because initially, an untrained network might just look at a picture of a dog and confidently guess that it's a toaster. Well, initially, it doesn't know. A brand new neural network is basically a stupid brain. It starts with totally random weights and completely random biases. To fix this, we use a brilliant mechanical process called backpropagation. If the feed-forward phase is the network taking its best guess, backpropagation is the network learning from its mistakes. The system calculates exactly how wrong its guess was, its error or its loss, then it sends corrective signals flowing backward through the entire network, almost like a ripple effect in a pond. As this signal washes back, it tweaks and adjusts thousands of those mathematical dials, the weights and biases, just a tiny infinitesimal bit. So the very next time it sees that image, its guess will be slightly closer to dog and slightly further away from toaster.
The actual optimization of these weights is driven by an algorithm called stochastic gradient descent. And a wildly important part of this whole shebang is the learning rate. The learning rate dictates exactly how aggressively the network changes its mind after making an error. Think of a high learning rate like a panicked student cramming for an exam. They make snap judgments, wildly change their answers, and just end up horribly confused. But a low learning rate is like a stubborn student who refuses to change their mind at all, taking absolute ages to learn a single new concept. Setting the learning rate is a super delicate mathematical balancing act to gradually, methodically minimize errors without overcorrecting.
Section 4. Why this matters today.
Let's bring everything we've just learned all the way back to the macro level. We've seen the micromath, the feed-forward assembly line, and the backward learning ripple effect. When you take these microscopic operations and multiply them by millions or even billions, happening at blinding, unfathomable speeds, the real-world impact is nothing short of revolutionary. By slightly altering the architecture of these networks, we literally change the world. We use convolutional neural networks, or CNNs, to process spatial grids of pixels. This specific grid structure is what allows self-driving cars to see the geometry of the road and doctors to detect tiny, anomalous pixels in medical imaging. On the flip side, we use recurrent neural networks, or RNNs, to process sequences of data over time. This gives us voice assistants that actually understand the chronological flow of our speech, and models that predict dynamic, complex weather patterns. Yet, whether it's a grid or a sequence, it is all built on that exact same microscopic foundation of processing simple inputs using weights, biases, and activation funnels.
We've journeyed all the way from a single tiny math equation to massive systems that literally power the infrastructure of our modern world. It is genuinely astonishing to realize that this intimidating black box is, at its core, just layers upon layers of simple arithmetic, learning from its own mistakes. But really, understanding this leaves us with an incredibly provocative question to ponder. If billions of simple math equations are enough to successfully mimic complex human intuition today, what exactly will they be capable of tomorrow? Thanks for joining me on this explainer, and I really hope you walk away seeing the artificial intelligence around you in a whole new, illuminated light.